Okay guys, welcome back to SQC tutorials where complex topics are actually made very easy. So for today we are going to talk about set laws, or the laws of your set. There are 7 basic laws of sets, and each of these laws have their children. They are broken down into several laws to suit your taste. So we'll start with the first law and the second law, then we'll move over to every other law. So the first law is the commutative law. When you talk about commutative, we are saying if you can swap it, if something is true when you change the order. Now we have A intersect B. Will it be true if I change the order to B intersect A? So basically, when talking about commutative, we are actually comparing two things to know if you swap the order, if it is true. It's just like saying 1 plus 2 is 3. If I change it to 2 plus 1 instead of 1 plus 2, will it still give me 3? That's what commutative law is all about. You are comparing two things. So we want to verify if the commutative law is actually correct. If A intersect B, is B intersect A. Now there's no need for me to go through the Venn diagram. The intersection of two sets, A and B, is actually those elements they have in common. So the element that A and B have in common is A intersect B. Let's check for B intersect A. It's still the same thing. The elements that B and A have in common is actually the intersection of B and A. So this first law is already verified. There's no necessary proof for it. What about A union B? The union of two sets is adding the elements of the two sets together. So when you have A, you list out the elements of A and add it with the elements of B, you will get the union of A and B. Now when you choose to list the elements of B first, then before adding the elements of A, the new set you get will still be the same as this. So it means that the union of A and B is the same thing as the union of B and A. So this second one is verified. So for the third law, we have A symmetric B and B symmetric A. Now A symmetric B are those elements that are in A but not in B, and adding it up with those elements that are in B but not in A. So let me quickly do that with Venn diagram. If this was A and this was B, A, B, and this is A and B, asymmetric B are those elements that are in A but not in B. So the elements that are actually in A and not in B is this part of the Venn diagram. And adding it up with those elements that are in B but not in A. The elements that are in B but not in A is this part. Now we want to verify if it is the same thing as B symmetric A. Now B symmetric A are those elements in B but not in A, those elements in B but not in A, and adding it up with those elements that are in A but not in B. So if I add it up with elements that are in A but not in B, whatever I get here is actually the same as this. This part is not among. This intersection part is not among. So it means that the symmetric difference is actually commutative. Now let's move to the second law, the associative law. Now we want to verify if you have A intersect, open bracket, B intersect B. If it is the same as A intersect B, then intersect C. So let's start the verification now. Now in associative law, we are comparing 3 sets and we are using one set operation at a time, in the sense that we have intersect, 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 intersect. So we are working with one operation at a time. That's what associative law is all about. If one operation is actually versatile enough for you to change the order, that is what associative law is all about. So we want to verify if this is this. So the first one, we have 3 sets. Let's say this is the first set, this is the second set, and this is the third set, A, B, C. And let's say this is for the other side of the equation. This is this, this, this. Okay, before I talk about these two, let me talk about, now we said there are 4 basic set operations. the union, intersect, and the difference before the symmetric difference. Now you must note that A minus B is not B minus A. This is because the difference between A and B, that's A minus B, are those elements in A but not in B, while these are those elements in B but not in A. So we have two different sets. So these two things are not equal. So you could take this as a fourth commutative law. So let's check for this particular one. Now we want to first of all do B intersect C before we do A intersect everything. Now this full circle here is your B, and this other circle here is your C. What will be B intersect C? It will be this point here, because we are picking the elements they have in common. Now after doing B intersect C, we want to now intersect it with A. That means, what does this full part have in common with A? It is actually just only this part. Only this part. So it means that A intersect, open bracket, B intersect C is actually just this small part here. Now let's check for the other side of the equation to verify if it will give us the same thing. Let's first of all look for A intersect B. Now if this is A, B, C, we want to check for A intersect B. This is A and this is B. When you intersect them, the two parts they have in common is just this place, like this. Now this full part, you want to intersect it with C. You are joining it with C. You are joining it with C. So what they will have in common, this full part like this, we have only this smaller part in common with C. So this is what you get, which is the same as this. So this has been verified to be true. Now what about the union? This one you don't need to even draw your Venn diagram. If you have B union B, you are adding B and B union C. You are adding B and C, then adding it up with A. So everything here. Then if you are adding A union B, you are adding A union B. Then you are adding it with C. You get everything here, which will be the same. So this one is also verified. Then what about asymmetric B, asymmetric B symmetric C, or asymmetric B symmetric A? So let's quickly verify if it is correct. So basically, B symmetric C are those elements that are in B but not in C. So it includes this part, those elements in B but not in C. So these are the elements that are in B but not in C. Then adding it up with those elements in C but not in B. So these are the elements in C but not in B. So we have gotten B symmetric C. Now we want to check for this whole part symmetric A. It is those elements that are in A. Let me redraw it like this. I want to compare it with A. So I want to compare this shaded region with A. Symmetric difference of this and this. So it is those elements that are in A but not in this part. Those elements that are in A but not in this part. So the elements that are in A but not in this part is actually this place and this other smaller part, since it's a part of A but is not in this part. So I'll add this point to it. So we have gotten the first part. Then those elements that are in this part, adding it up with those elements that are in this part but not in A, adding it up with those elements that are in this part but not in A. So the elements that are in this part but not in A, we include this side, but this part will not be among. So I'm going to add here. So this will be our A symmetric, B symmetric, C. We have verified this, that this is how the diagram will look like. It will include all the circles apart from all these other smaller parts. So let's check it if it will be the same with this other part of the. So let's verify with the second one. We have A, B, and C. First, we want to look for asymmetric B. What will be asymmetric B? Those elements that are in A, but not in B. So these are the elements that are in A, but not in B. And what will be adding it up with those elements that are in B, but not in A. So these are the elements in B, but not in A. So we have gotten the first part. Now we want to compare it with C. So it is those elements in this region that is not in C. Let me do that here. Let me do that here. So it is those elements that are in this region, but not in C. Those elements in this region, those elements in this shaded region that is not in C, then adding it up with those elements in C that is not in this region. So first of all, the elements that are in C but not in this region is this shaded part and this smaller part. So let me shade here and this smaller part here. Then what about those elements that are in this region but not in C? It will include this part but not this smaller part. It will also include this part but not this smaller part. So I'm going to have this, which is the same as what we drew here before. So it means that this is very true. So that will be all for the first two laws of sets. Let's move over to the third law. Welcome back from the short break. Now let's move over to the third law, the distributive law. Now for the distributive law, we are also comparing three sets, but we are not using one set operation, unlike our associative property. Now we are comparing three sets with two different set operations. It could be intersection and union. It could be union and intersection. It could be union and symmetric difference. It could be symmetric difference and intersection. But don't bother trying difference. That is A minus B if it is distributive. It is not. Or you can as well try it and state it in the comment section how you went through about everything. So we want to verify if the distributive law, if intersection is distributive over union, and if union is distributive over intersection, and if intersection is distributive over symmetric difference. And you can as well try if symmetric difference is distributive over union or vice versa. So I want you to try that and state in the comment section what your result is. But these are the three basic distributive laws. So let's kick off and start verifying these laws. So for this, we want to first of all do B union C, then intersect it with A, then we'll compare it with this if we get the same result. So this is your A, B, and your C. A, B, C. So let's compare. Let's do this first. Now, first of all, we'll do B union C. So B, adding the elements of B with C. So let me add them quickly. I have B union C. Adding it to the elements of C. So this is what I will obtain. Now I've gotten my B union C. Now I want to intersect it with A. What part does this shaded region have in common with A? It is just this part like this part. So the common part is this point like this. The part that this B union C have in common with A is just this shaded region. So we have gotten the first side of the equation. Now let's compare it with this second side of the equation. We have the first one. And lastly, we have this. A, B, C. A, B, C. A, B, C. So let's compare if what we will obtain here will be the same, the shaded region we will obtain here, if it will be the same with this one. So let's compare. Now we are looking for A intersect B first. What will be our A intersect B? The elements that A and B have in common, it will be this shaded region. Then we are looking for A intersect C. A intersect C. What will be A intersect C? The elements that A and C have in common. So it will be this shaded region. Now we have gotten our A intersect B and our A intersect C. Now we want to add them together. When you add this region and this region together, what you are going to get is this region, which is the same as this shaded part. So the first distributive law has been verified to be true. And whenever you have A intersection of something like this, you can open the brackets and put A intersect B first, then the union of A intersect C. It's more like opening your brackets. So let's move over to the second distributive law. Let's verify if this is correct. So first of all, let's do A union B intersect C. So the first thing is to do B intersect C first of all. What will be our B intersect C? The elements that B and C have in common. The elements that B and C have in common are these elements. These are the elements they have in common. And you are adding it up with A. You are adding it up with A. So you are joining A intersect B intersect C, which is this part, and adding it up with A. So what you get is this region. So we want to verify if this is the same as this. The first thing is to do A union B. What will be our A union B? Our A union B are the elements of A, adding it up together with the elements of B. So these are the elements of A, adding it up with the elements of B. So this is A union B. What about A union C? This is A, B, C. A union C. The elements of A, adding it up with the elements of C. So this will be the elements of A, adding it up with the elements of C. So lastly, we now compare A, B, C. Now let's find this shaded region and this shaded region. We want to find their intersection. What do this shaded region and this have in common? The parts they have in common is they have this part in common first. They have this part in common first. They also have this other part in common. They have this part in common. And if you observe closely, they have these other parts in common. So let's compare with this. If you observe closely, this shaded region is the same as this shaded region. So the second distributive law has been verified to be very true and correct. So let's check for the third distributive law if it is true and correct. We have our A, B, C. What is B symmetric C? the elements in B that are not in C, those elements that are in B but not in C, these are those elements that are in B but not in C. Then adding it up with those elements that are in C but not in B. So you're adding it up with these elements. You're adding it up with these elements. Now when you intersect this shaded region with A, the only region they have in common with A is actually just this small spot and this small spot. The only region they have in common with set A, the only region that this shaded region have in common with A is this small spot and this small spot. So the shaded region becomes this part. So we want to verify if after doing this, if we are going to get the same shaded region as this. So let's kick off. So we have our normal ABC. Let's first of all look for A intersect B, the elements that A and B have in common. These are the elements that A and B have in common. So we have gotten this. Then let's look for A intersect C. A intersect C. So these are ABC, A, B, C. The elements that A and C have in common is this region. What about when you now take this region and you want to do the symmetric difference of this region and this region? So the symmetric difference of those regions are those elements that are in this region but not in this region. The elements that are in this region but not in this region is actually just this shaded part. They are the elements here but not here. What about the elements that are in this region but not in this region? Is just this part, which is the same as this. So the third distributive law has been verified to be very true. So that will be all for this video. In our next video, we'll talk about the last 4 set laws and we'll wrap it up there and start solving set problems. Thanks for watching. Please do not forget to like and subscribe to our YouTube channel and share this video. Your success is our concern.